Hello everyone, today we'll talk about the solution to the problem height of binary tree after subtree removal queries. This problem is classified as hard, and it also has this word queries in plural here, but don't worry, we don't have to, after every subtree removal, change the state of the tree, and so subsequent removals would have to operate on a changed tree. That's not the case here. In this case, whenever we have a query, we answer the height of the tree after this query, after removing a subtree, and we get back to the original tree. So queries are independent. That makes this problem much easier than if the question was to persist changes step by step. Every query were to permanently change the tree. So there are probably multiple ideas when it comes to solving this problem. One easy observation that can lead us to those ideas is the fact that at every level of the tree, so let's say that we have a tree, we have some one deepest path to the deepest leaf. And let's say that we are looking at some level. So we have this node on this level in whose subtree this deepest path exists. So certainly if we want to change anything that's not in the subtree, so let's say that we are changing on this level, removing a subtree. So if we're removing some other subtree, the depth of the tree doesn't change, because still this deep path was the deepest originally and it is still the deepest. And the only thing that can change if we do something in the subtree of this node that holds the deepest path. And in that case, we have to remember the second best node, the node where the second deepest path exists. Maybe that second deepest path is equal in length to the deepest path. But that means that at every level, we only have to remember the best choice and the second best in case the best choice is touched by our query. And that also might lead us to different ideas for a solution, but in particular, one thing that we can do is we can, in a simple recursive way, by knowing the level at which we are and the depth of every node in the tree, or the height of every subtree in the tree, then let's say that we are currently at a given node, it has some two subtrees, and we want to be able to calculate the answer for every node in our tree. Of course, it had some parent, and something's happening above it. Well, first of all, what is the answer when we remove the subtree rooted at this node? Well, the answer is maybe, when it comes to its parent, the depth of its parent plus 1 plus the depth of the subtree in the other child, or maybe we have to go one level up, and then we have again the depth of a child there, plus the level, and so on. So that would be the answer when we remove this node. And this we can assume that we have pre-computed before. We have this pre-calculated. And now, when it comes to calculating the answers for the children, for the two subtrees rooted at this node, then the answer for this subtree is either the same answer that it was for its parent, so all of that, because still after removing this subtree, we cannot get anything that's worse than after removing this whole subtree. So all of that is still in contention to being the best. But there is also another way, and that other possibility is that we look at the height of the remaining child plus the depth of that child, and that might be even better than going upwards. So again, we have to remember the value that will be the answer if we remove this whole subtree, which at the beginning the answer would be 0 when we start at root, and afterwards whenever we descend to the left or right subtree, the answer is based on the height of the remaining subtree. And of course the base case for our recursion is when the tree is empty. So let's see the code. To calculate height, you can do it however you want. The general pattern for height is that if we are at a null node, the answer is 0. Otherwise, we take the height of the left and right children and add 1 to it, to the maximum of those two. So we calculate height. To be able to reference that height later, we just use the cache decorator. It's essentially the same as if we were to create a dictionary, and in that dictionary save the answers when we were calculating them. This is the same thing that we'll be doing in our recursive function. We'll be remembering in the dictionary the answers for every value, for every node. We can't easily do it using this cache decorator because we don't want to remember those auxiliary values, so the level and the current max. We don't want to remember them, we only want the key to be the value of a root. So we don't have to do anything when we run out of the tree, so when we are at an empty tree. Otherwise, we know that the value that we're passed from above is the answer for our current node. So we remember that in this memoization dictionary for the value of our root. So this corresponds to the fact that we've reached this node. So the answer is calculated here. So this is the v that's calculated for the rest of the tree. And now we have to calculate the answers for our left subtree and our right subtree. And of course it has level 1 deeper. And the answer can be either the same value that it is for us. So this corresponds to the fact that even if we remove only this subtree, the best answer can still be the same as if we remove the whole subtree. So the answer is in the rest of the tree. But maybe the answer is in the other subtree. So in that other subtree, the answer would be the level of the current node plus the height of that subtree. So when we go to the left, so when we calculate the answer for the left subtree, then we know that the right subtree will exist in the tree after the query, so we can use its height. The same thing when we calculate for the right subtree, we can use the height of the left subtree. Of course, we have to run it at root, starting at level 0 and with value 0. And at the end, in memo, we have calculated the values for every node. So now, since we have those independent queries, we just return the answer for every value in those queries.